Alright, so you should be at this page. We're going to start on this homework video by looking at taking the derivative of trig functions. And then also, the other part of this, so I think this is standard D7. We're also going to be looking at D8, which is the chain rule, which is one of our most versatile rules that we have to take derivatives in calculus, so we do practice a lot with it. So let's start by looking at the derivatives of sine and cosine. We've kind of already touched on this a few times together, like when we were looking at derivative graphs and we would graph the derivative graph of what looked like a sine function. It ended up being another sinusoid. So the derivative rule, and this is, I'm going to kind of write it here, this notation means the derivative of sine is actually cosine here. Alright? And the derivative of cosine is negative sine. Okay, so unfortunately it's not like a straight, flip-flop, but it's pretty close. Derivative of sine is cosine, derivative of cosine is negative sine. We get into the other functions down here, but first, before we do that, well, you know what? Actually, I was gonna make you prove the sine derivative. I'm not gonna do that because it's not on our standard. I can show you where it is in the book. We can talk through it, and actually, I probably will talk through it tomorrow. But in terms of writing your notes, I don't want you to think that you have to be able to do that. It's just to show you that, like, this conversion to get from sine, derivative of sine to cosine, does happen in a logical way, like if you use the limit process, but I'm not going to make you do all that work here. So I'll just give you the straight derivative rules. The derivative of tangent is secant squared. The derivative of secant is secant tangent. The derivative of cotangent is negative cosecant squared. And the derivative of cosecant is negative cosecant cotangent. Now, a couple of things to, didn't realize you couldn't see that. A couple of things that you will want to pay attention to here to keep it straight. Anything with a so cotangent and cosecant, the derivatives have the co-functions in them as well. You have cosecant squared, cotangent, cosecant. Also, the co-functions, their derivatives have the negatives. With the other two, they're positive. Now, there are reasons for all of that. They have to do a lot with the graphs, and where tangent is increasing, secant is decreasing, and we will look at some of that as we go. But for right now, what we need to use this stuff for is just to take derivatives. So, we're going to use these rules. You do have to have these rules memorized, but we'll use them enough that you do get used to them. But sine and cosine is by far the most common. Okay, so let's look at example 1. Let me find my little example here. Alright, let's start with making an A, a B, and a C. Alright, the first one that we're going to look at is y equals x minus tangent x plus 2x squared. Okay, so we have a linear combination of functions here. You have a linear function, you have a tangent function, and you have a quadratic function. To find the derivative of this whole function, you take the derivative of each piece. So the derivative of x is 1. The derivative of negative tangent is negative secant squared. And the derivative of 2x squared, is 4x. Okay, for B, here's another one. Okay, we're just practicing using some of these rules. Y equals. Okay, so to take the derivative of this, you're going to take the derivative of each piece. The derivative of the first piece is going to be negative 12x to the negative 4. The The derivative of cosine is negative sine. So since there's a negative there already, you're going to end up with a positive sign. The derivative of 2 is 0. So you just end up with a function that looks like that. Okay. Let's look at one more. So notice here I'm starting to mix some functions. I'm starting to throw in some trig functions with power functions. Alright, the derivative of 2x to the 2/3 would be 4/3 x to the negative 1/3. The derivative of sine is cosine. And the derivative of negative cosecant is negative cosecant x cotangent x. So since there's two negatives there, we're going to make that a positive. Okay, so example 1 is just practicing with the basic rules and what they would look like in a problem. What I really want to focus on for today's video and what we're going to really focus on tomorrow is the chain rule. So today we're going to also cover another major rule of differentiation. This is one of our most helpful rules because it's kind of a shortcut, so we don't have to simplify everything before we take the derivative. And a function where we would use this shortcut would look like this, where you have f of x equals sine, and then in the argument you don't just have x like you had up here, but you have another function. You have an x squared. A function that looks like this is called a composite function. It's composed of at least two different functions. The x squared in the parentheses is called the inside function, and the sine function on the outside is called the outside function, for lack of better terms. So suppose you set out to take the derivative of y equals sine x squared. Well, most of us, when we go to take the derivative, we say, okay, well, the derivative of sine is cosine. And so then it's just cosine of x squared. However, when you check the numerical derivative on the calculator, you see that it's not true. Okay, so we're going to actually do that. So if we were to graph sine x squared, let me check my mode here. So we have sine x squared. And then what we think is the derivative, cosine of x squared. And then we're going to sketch the numerical derivative. And if we're correct, the numerical derivative should line up with the derivative we found. And a little hint, this is a way that you can check your work as well. I'm going to go ahead and trace that with a bubble. Okay, so when we graph, oh dear. Okay, so that's my sine of x squared. Okay, we need to quit that. Let me adjust my window here. Let's go from -1 to 1, -1 to 1, or let's say -5. We'll go up by 0.5. I just want a better picture here. Okay, a little bit better. Okay, so there's the original. There's the derivative that I think should be the derivative. And then there's the actual derivative. Notice it's graphing so much slower, but that's because it's calculating the numerical derivative at every x value. Okay, so you can see that the darkened portion, which was what we thought the derivative should be, just by intuition, and the actual numerical derivative, they look nothing alike. So what we can take away from that is that this is not the actual derivative function of this. This happens because the cycles of y equals sine of x squared occur more frequently as x increases. The derivative function actually is cosine of x squared times 2x. The anticipated result, cosine of x squared, which is what we would logically think would be the derivative, is multiplied by the derivative of the inside function. So the derivative of x squared is 2x. You can use the chain rule, and that's actually what this identifies with. You can use the chain rule to differentiate composite functions. To see why the chain rule works, realize there are really three functions involved in this. You have the inside function x squared, you have the outside function sine, and then you have the whole entire function all at play. Each one has its own derivative. And so you can kind of see if you have three different functions, x squared, sine, and the composite function, each of them have different slopes at the same point of 1. Here. So observe that y depends on u depends on x. The derivative of u with respect to x, 2x is the slope of the x-2 graph. Okay. Oh, which one did it say? Y depends on u and u depends on x. Okay? So y depends on what this, oh, you can't even see the graph there. Y depends on what this inside function is, or the u. And then the derivative of u depends on, or sorry, the derivative of this depends on what u actually is. Maybe that's not a very good explanation. I'm sorry. If you looked at this like a function and took the derivative of this, that's what it's referring to. So it's saying that this slope is the derivative of this, but then this connects with this function, and then you have a new slope, and this connects with this function, which gives you a combined slope. Okay, so the connection there being that you have three different things going on, each one depends on the other, and each of the derivatives are connected. The phrase with respect to u means that u is the independent variable. So it's saying basically here that x is not my actual independent variable. U is actually my independent variable because u represents this function inside. The derivative of the composite function is the limit of the two separate derivatives multiplied together. Now, you have the chain rule so that you don't actually have to find the derivative and then multiply them together and then find the limit and all of that. The chain rule kind of takes care of it for you. Okay, so let's go down to here. The reason it's called the chain rule is because if you have several inside functions, the resulting derivative looks like a chain of all the separate derivatives multiplied together. So what this looks like in terms of writing out the chain rule, we would say, okay, if f of x equals g of h of x, then the derivative of f is the derivative of your outside function. Okay, so notice the inside function did not change here. You just took the derivative of the outside function, and then you multiplied it by the derivative of the inside function. So you have outside, inside. Okay, more simply put, because I like to use u substitution, which we'll get into. If f of x equals g u, this inside function, then f prime equals g prime of u times u prime. Okay, so just two different notations, and I'm going to start using u as a variable more and more often because u substitution is something we have to use when we get to integration. And so if you're already comfortable using it in terms of deriving things, you're going to be a little more comfortable with it. Okay, so inwards. And I know I'm stressing this like three different ways, 3 different times, but this is, again, one of the most used derivative rules that we have. To differentiate a composite function, take the derivative of the outside function, and then in parentheses, the inside function does not change, and multiply it by the derivative of the inside function. Okay, so let's do a couple of examples together here. Make an A and a B. First one, I'm going to start you out pretty easy. Cosine of x cubed. Okay, so we have to determine, first of all, what the inside function is. Well, the inside function here would be x cubed. So maybe I'm going to let u equals x cubed, and u is the inside function. Okay? So g prime of x, if I'm trying to take the derivative of this function, I'm going to take the derivative of the outside function. So the outside function here is that cosine. The derivative of cosine is negative sine. So you take the derivative of the outside function. Notice my argument does not change yet. And then I chain on, or attach by multiplying, the derivative of the inside function. So the derivative of the inside function is 3x squared. Okay, so that piece there is the derivative of the outside, and this is the derivative of the inside. And I should have, sorry, here, never mind, we'll leave it as is there. Okay, and then let's look at another one. H of x equals tan to the fourth of x. Now, let's talk about this. This is a little sneaky at this point, but you'll get better at recognizing it. You have two different functions going on here. You have tangent, and then you have this power of 4. You can write this, and I actually recommend that you rewrite it so it looks like this. It's the same thing. It's just where the power is makes it a little bit easier to see what to do. Technically, this, if we let u equal tan x, okay, and then the derivative of u, since I know I have to take the derivative of the inside function, and this is my inside function here. I know it's my inside function because it's inside this function of power of 4. The derivative of tangent is secant squared x. Okay, so when you take the derivative, and this is why I kind of wrote it like this, when you take the derivative in terms of u, you take the derivative of the outside, so g prime of u times u prime. U prime can also be written as du. This represents the derivative of u. Alright, so we're going to rewrite this so it looks like this. Okay, so we're going to let u equal tan x, and then we're going to use some substitution here and make it u to the fourth. You've been taking derivatives of functions that look like this all the time using the power rule. Okay, and then we multiply by the derivative of the inside function. So we have h prime of x equals 4. My u is tan x cubed, and then you have to attach your derivative of your inside function. You don't have to necessarily use the u substitution. The only reason I'm kind of introducing it here in this section is because the more comfortable we can get with this and using it to substitute in and then rewrite at the answer at our final step, the smoother integration is going to go later. So this is just warming you up to it a little bit. But if this is more confusing at this point for a chain rule, then go from here to here. The outside function is 4, so you would take that power of 4 multiplied on the outside, reduce the power by 1, which is what we have here. The inside function does not change. And then you chain on or multiply by the derivative of the inside function. So this would be your derivative. Okay. Let's look at time here. 20 minutes. Let's do a couple more. I don't remember how many examples I have for this. Alright, for example 3, make an A and a B. And then write that as your function. Alright, and then we're going to go ahead and we're going to let u equal the inside function. Now when you have powers going on, that usually indicates you what the inside and outside function actually is. In this case, my inside function is that x squared plus 3x minus 7, and then the derivative of that I would have to chain on at the end is going to be 2x plus 3. Okay, so again, I'm going to use substitution here. Alright, so I'm taking my inside function and I'm going to, at least for the time being as I find the derivative, let u replace it so it looks a little bit nicer to use. And then we're going to take the derivative of that. Well, that's just a power function, so I'm going to bring the negative 5 out, reduce by 1, and then multiply by the derivative of u. Because we're chaining on, since I know that's an inside function. And then we're just going to rewrite by plugging what u is back in. So I know u is that x squared plus 3x minus 7. Now you're chaining on the derivative of u. Now be careful there. You should make sure you put that in parentheses. Otherwise, if you had to use it for something, you wouldn't be able to. Okay, now let me tell you why this is a lot nicer to use for the chain rule. Because when you have a power, what we would normally have to do here in this case is we might have to flip this on the bottom and then multiply this by itself 5 times and then take the derivative somehow. And that gets really complicated and long when you have to start simplifying stuff that looks like that. But using the chain rule, if you can identify an inside function and outside function, you're going to shorten your work here and actually have a nicer answer to work from if you need it. Alright, let's look at one more together. And then I'll probably do example 4 and 5 with you tomorrow. So let's look at y equals 24 sine to the 5/3 of 4x. Okay, and we're going to do a little work here on rewriting. You actually have 3 different functions going on here. You have an outside function, an inside function, and then an inside-inside function. Now this 5/3 is attached to the sine, so I'm going to start by rewriting this like I did that tangent function on the other side. My argument is 4x, but I'm going to put that power on the outside. My outside function is this power of 5/3. My inside function is this sine, and then my inside-inside function is this 4x. So, knowing that, we're going to work piece by piece. You start with the outside function, and so maybe I'm going to let u be my inside function. My inside function is that sine of 4x. Then my du is going to be cosine of 4x times 4. Because I have to take, taking the derivative of sine of 4x, you have to use the chain rule there because your argument is not just x. So that would be du. And I'm going to rewrite in terms of u. Okay, so we replace the inside function with u. And I'm going to take the derivative, which would be 40. Okay. And times du when we take the derivative. And then we're going to replace everything with what it's actually equal to. So we have 40 sine of 4x to the 2/3 times, and actually, yeah, we'll chain that on like that. So cosine of 4x times 4. So this is the outside, this is the inside, and this would be the derivative of the inside. So technically you could probably go on forever and ever and just have more inside functions, but taking the derivative of something where you can have the inside and outside function situation going on, you would just start multiplying and kind of work your way from the outside function, which in this case was 2/3, and then kind of narrow in until you get to the very last inside function. And that would be your answer. Now I know we could simplify that a little bit by bringing that 4, since all of these are being multiplied, you can make that 160, and it would still be correct there. But I wanted to show you the breakdown of the derivatives. You have 3 derivatives chained there together. Okay, and And then this is where we'll pick up tomorrow as a warm-up or before I have you work together on the chain roll stuff.